Okay, good morning, all of you. There is always light after dark. Okay, so this hope only we have to keep always in mind, and we always have to get spirit from that. And today's quote is, nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less. So the more you understand, the more you will be free of fear. And there are two birthdays today who are familiar to you. One is Mendeleev. So, I think, who is Mendeleev?
Father of whole and periodic table.
Periodic table, right? Mendeleev means periodic table. He was a Russian chemist and inventor. He is best known for formulating the periodic law and creating far-sighted version of the periodic table of elements. He used the periodic law not only to correct the then accepted properties of some known elements, such as the valence and atomic weight of uranium, but also to predict the properties of three elements that were yet to be discovered. So that is the real great thing about Mendeleev. So when he has created the periodic table with some imagination that there should be some symmetry in nature. And so he found the gaps and he predicted that there will be some more elements we are going to find out, and he found out the properties of them also before finding the elements. That is the great thing. He has predicted the principles of three elements that were yet to be discovered, like germanium, gallium, scandium. They were not there at that time. But he predicted these types of elements will be discovered soon. Okay, so he says science which deals with the infinite is itself without bounds. And so there is another person, Bernoulli. I think all of you are familiar, Daniel Bernoulli. Actually, Bernoulli's family is there. There are many people who are mathematicians and scientists. So he's a French mathematician who was the most distinguished in the second generation of the Bernoulli family of mathematicians. His talents were broad. So you can see his talents, including medicine, biology, physiology, mechanics, physics, astronomy, and oceanography. And Bernoulli's theorem, which he derived, is named after him. Put simply, it relates the pressure and velocity of a fluid, in effect, the application of conservation of energy. He won several prizes for papers on diverse subjects, including the tides, planetary orbits, optimal shape of hourglasses, and reducing pitch and roll of ships. And with his work, Daniel Bernoulli established mathematical physics. He was the first to show the advantage of resolving compound motion into motions of translation and of rotation, so which we have studied in the CFD. Okay, today we will discuss about consistency, linearization, and stability. And before going to that, we will see what we have done yesterday in the last class. So we have discussed about 2D parabolic solvers. And we have seen first we tried FTCS explicit method. And using that, the constraint or the stability condition narrows the delta t still more, because we got that d should be less than or equal to 1/4. And if it is 3D, d less than or equal to 1/6. So that is the restriction or constraint or the condition or the time step. So leaving that, if you go to implicit BTCS formula, and there we have found that if it is 2D, we are going to get a pentadiagonal matrix, which is time consuming and complex to solve. And if it is 3D, we are going to get a heptadiagonal matrix. So to avoid all these problems, we have to resolve to some other things, like Crank-Nicolson method if you take. And Crank-Nicolson method also will have the same problem, though it is of high accuracy in time, x direction and y direction, second order accuracy. But again, this also you will get pentadiagonal for 2D and heptadiagonal for 3D. So we have seen those formulae. So the next best option is ADA method. So in the ADA method, which is alternate direction implicit method, we will have implicit in x and explicit in y in first half time step, and implicit in y and explicit in x in the second half time step, so that in each time half time step we get only tridiagonal matrix. So we have to solve tridiagonal matrix 2 times in a particular iteration. So this is found to be quite comfortable and promising, and with less mathematical complexity and less time consuming. Okay, so this is again like a two-dimensional to the second order accuracy in all time, x direction and y direction. And we have seen shown that ADI method is like an approximate factorization of Crank-Nicolson. So in the Crank-Nicolson, whatever you get, if you make it two factors, so they are going to become ADI method by neglecting a small term there. So this is called ADI method is called as approximate factorization of Crank-Nicolson method. And fractional step method also we have seen. What we have done is we take only x derivative in the first half time step and y derivative in the second half time step, and both Crank-Nicolson schemes we use there. So again, we will get tridiagonal matrix in two half time steps. If it is 3D, we make it 1/3 step, like 1/3 steps in one single iteration. So in that way, I can extend ADA and fractional step methods for 3D flows. Okay, these are the things we have seen in the last class. So today we are going to talk about
So you can click on the hide button, sir, beside stop sharing.
Okay, this actually I have to duplicate it. It's okay, right?
Yeah.
So the first we have defined consistency. So in the consistency analysis, so actually we have a partial differential equation. We have written in the finite difference form. That is called as finite difference equation. So this finite difference equation is written from the partial differential equation by neglecting some truncation error. So if the truncation error approaches 0 as the step size approaches 0, then we call that this equation is consistent. This finite difference equation is consistent. So that's what the consistency analysis is defined as. So the finite difference equation should become the partial differential equation as the step size approaches 0. Okay. So or under what conditions? Okay. The conditions for consistency we have to find out. That is, which makes the finite difference equation to approach partial differential equation. So we'll see one or two examples. We have taken this equation, and so if I take FTCS scheme, right? So I will get okay, this is the way we got the FTCS scheme. So what we have to do is we have to substitute for TIN plus 1, TI plus 1, and TI minus 1n, the actual Taylor series expansions into that, and see whether the delta x tending to 0 approaches to the original equation. That's what we have to check. Okay, so TIN plus 1 is TIN plus, okay, 1 by delta t into TIN plus delta t tt plus delta t whole square by factorial to ttt plus delta t whole cube by factorial 3 ttt. Okay, like this I will get on the left side, and here I have to substitute these things. Okay, so is equal to alpha by delta x whole square into ti plus 1 as ti plus delta x dx plus delta x whole square by factorial to dxx plus delta x whole cube by factorial 3 dxxx. minus.
Sir, Tn will not be there, no, sir.
What is that?
In LHS, Tn will not. Tn, Tin plus 1 minus Tin by delta T.
Yeah, that's right. Minus Tin. Right, thank you. So minus 2 Tin and plus Tin minus delta x dx plus delta x whole square by factorial 2 txx minus delta x whole cube by factorial 3 txxx plus etc. Okay, so this is the way we get. So we try to simplify it. And here tin gets cancelled. So here also tin plus tin, 2 tin and minus 2 tin. Usually this will be cancelled in every scheme. And so here on the left side, delta t, if I divide, so delta t goes off, here delta t goes off, 1 delta t goes off here, and delta t whole square here. Similarly, on the right side, this delta x plus delta x dx minus delta x dx goes off, and delta x whole cube by factorial 3 minus delta x whole cube by factorial 3 goes off. Okay, and then we divide by delta x whole square. This delta x whole square, this delta x whole square goes off. Here 1 delta x whole square goes off. Like this. Okay, this is the way it will be. So what is that is left with? So tt plus delta t by 2 ttt plus delta t whole square by factorial 3 ttt is equal to alpha txx by 2 and txx by 2. 2 are there. So txx and plus delta x whole square will be there. 2 into delta x whole square by factorial 4 txxx will be there. Like this it will be. So if you see here, if delta t tending to 0, these two will be 0, and delta x whole square tending to 0, because later I will have delta x power 4, delta x power 6 like that. So these things will be 0. So I will be left with tt is equal to alpha txx as delta t tending to 0 and delta x whole square tending to 0. Okay, so this is the condition for consistency or the order of accuracy. Is it clear?
Yes, sir.
Okay.
No, sir.
So we will see another scheme, which actually I told there is one more thing will be coming into that. So, so if I take again tt equal to alpha txx, and I will take Buford-Frankel scheme. So this I have done, I told I have done small mistake there. Okay, this is nothing but modified CTCS. Okay, so here I will get tin plus 1 minus tin by delta t is equal to alpha ti plus 1n. So this is tin minus 1 also. Okay, this is central difference in time, tin plus 1 minus tin minus 1 by 2 delta t. Okay, and alpha into ti plus 1n minus 2 tin. So here I take it as the average of tin plus 1 plus tin minus 1 by 2. Okay, here this plus I have given as minus in the last class. That's the, okay, plus ti minus 1n. Okay, this is the way I will get by delta x whole square. So this alpha delta t by delta x whole square, if 2 delta t, if I taken it this side, I am going to get 2d. And this 2 and this 2 goes off. And tin plus 1, if I bring it to this side, 1 plus 2d, tin plus 1. is equal to tin minus 1. If I take it to that side, 1 minus 2d tin minus 1 plus 2d into ti plus 1n plus ti minus 1n. Like this I will get. Okay, so this also I will bring it to this side. So 1 plus 2d ti n plus 1 plus 2d minus 1 into ti n minus 1 is equal to 2d ti plus 1n plus ti minus 1n. Like this. Now I will check the consistency. So I will get 1 plus 2d into tin plus delta t tt plus delta t whole square by factorial to ttt plus etc. plus 2d minus 1 and tin minus delta t tt plus delta t whole square by factorial to ttt plus etc. plus is equal to 2d into ti plus 1n. So tin plus delta x tx. I can show you this. Actually, it is there in the slide also. I thought if I do it, you will understand it better. Minus delta x dx like this I will get. Okay, so if I take tin terms, here 1 plus 2d tin, 2d minus 1 tin. Okay, if I add these two, I will have 4d tin. And on the right hand side, here 2d tin, here 2d tin. It is plus or maybe this is plus. Okay. So 4d tin on both sides. So this tin, this tin, this tin, this tin gets cancelled. Okay. And for delta t tt, so I will have 1 plus 2d plus 2d minus 1. So how much? And okay, minus 1 plus 2d minus 2d minus 1. 1 plus 2d plus 1 minus 2d. So I will have 2 delta t tt. And for delta t whole square, this is 1 plus 2d plus 1 minus 2d. This will become 4d. Like this I will get. So is equal to on the right side. So delta x 2x tx and delta x dx goes off. And so 2d into 2 times delta x whole square by 2 txx. Delta x whole cube gets cancelled. So plus 2 times delta x whole power 4 by factorial 4 txxx. Like this I will get. Okay. And now if I write this d as alpha delta t by delta x whole square, and this 2 and this 2 goes off. And so 2 I can cancel on both sides. So this 2 can be cancelled, and this will be 2 here. And this 2 and this 2 gets cancelled. So I will have delta t tt plus d into means alpha delta t by delta x whole square delta t whole square ttt is equal to alpha by delta x whole square into delta x whole square dxx plus delta x to the power of 4 by factorial 4 dxxx. Like this I will get. Okay, so here if I, here delta t also is there. So this delta t, this delta t, this delta t goes off. And this delta x whole square, this delta x whole square, and this delta x whole square goes off. So I will be left with tt plus alpha delta t by delta x whole square ttt is equal to alpha txx plus 2 into delta x whole square by factorial 4 txxx, like this. Okay, this will be like this. So here, this delta t by delta x whole square will come into picture. Okay, this is delta x whole square will be there. So like that, I'll have the consistency condition delta t and delta x whole square and okay, even if it is not there, no problem. Delta t by delta x whole square should tend to 0. Okay, this additional thing will come into picture. Okay, what is this? If delta x is tending to 0 or delta t tending to 0, why not delta t by delta x whole square naturally may tend to 0, like that you may feel. But here delta t should tend to 0 faster than delta x tending to 0 to make delta t by delta x whole square tending to 0. Otherwise, it will have some finite value. It will be something like this. I will have pt is equal to some alpha k square tt so it will be something like this. If delta p delta x whole square, instead of tending to 0, if it is tending to some finite value, then this will have this form. So I am solving a equation, and this is, if you see, this is hyperbolic. I have txx and ttt is there. So this is hyperbolic. So I am, instead of solving a parabolic equation, actually I am solving a hyperbolic equation, and I am not solving the original equation, which is tt equal to alpha txx, but I am solving this particular equation. If delta t by delta x whole square is not tending to 0, and if it is tending to a finite value, that is, it happens when delta t tending to 0, if it is faster, then delta t by delta x whole square tends to 0. But if delta x tends to 0 faster than delta t, then it will have a finite value. Is my logic clear? Okay, so this is what I wanted to express. So this is the way we check the consistency.
So once can you go to FTCS?
FTCS, there will not be problem.
No, the slides.
Yeah, this is FTCS.
This is CTCS.
Yeah.
Sir, here we wrote the delta x square tending to 0, right? Like,
yeah,
which is mathematically correct? Delta x tending to 0 or delta x square tending to 0? Because in the
here, because I am here I have delta x whole square, here delta x power 4, like that. So I write delta x whole square tending to 0.
I mean, here it is okay, sir, but at the definition of when we define the central scheme,
it is given that the
delta x tends to 0 in the definition of central scheme.
Yeah, it is the step size approaches 0.
Yes, sir.
Yeah. Okay, if delta x whole square tending to 0 means okay, delta x tending to 0, delta x whole square tending to 0. This is okay, but if I have the ratio, then there will be problem.
Oh, okay. Like, sir, in the definition of central scheme, we write it as limit delta x tends to 0 and all. Sir.
Yeah.
I mean, there we are defining delta x is already 0, tending to 0.
Yeah, when you define the scheme, So we define like that only.
Yes.
But when we have the combination of this particular term and this particular term, then this additional term will come into picture. So this is tt is equal to this as delta t tending to 0. Txx is this as delta x whole square tending to 0. That is okay.
Yes.
But when I have combined these two, then this additional thing is coming.
Like why my question is coming is, if we tell delta x tending to 0, then delta x whole square is definitely 0. But if you are telling delta x whole square tending to 0, then delta x is not 0. Right? Not tending to 0.
Yeah, that's true. Okay, so then I will go to the next concept, what is called as linearization. So when I have a nonlinear term, if I have nonlinear term, I cannot use this the equations, that algebraic equation that you get. So I am writing tin plus 1, ti plus 1 and like that. But you may get square of it if it is nonlinear. So if I have square terms there, so I cannot use this Gauss-Seidel method or Gauss elimination method, those things. So I should have linear, that they are linear simultaneous algebraic equations. Then only I can use that. Otherwise I have to use some Newton's iteration method. There are other methods to solve nonlinear equations, but I want linear equation. So when will you get the nonlinear term? In the convection term. So there, for example, we get what is called as u dou u by dou x. This is a nonlinear term. So how to handle this? Suppose I am discretizing at I plus 1. So I am going to get ui plus 1 into dou u by dou x. I will write it as either ui minus 1 or ui plus 1 minus ui plus 1 minus ui delta x. Suppose, because this is upwinding, ui plus 1 depends on ui. Okay. So if I write in this way, I'm going to get ui plus 1 square, which is nonlinear. Okay, so what should be done for this? So there are methods, like one is lagging. So this ui plus 1, instead of taking ui plus 1, I take the value at previous station. That is, I write it as ui, and this will be ui plus 1 minus ui only. So if I take this way, this is what is called as lagging. So I am taking this value of u, instead of at I plus 1, I am taking one lagging behind. Okay, so this is what is called as lagging. Now this becomes linear only. Okay, so it introduces some error, of course, but it will solve the problem. This is one method. The another method is called as iterative method. So what we do is ui plus 1 k plus 1 and ui plus 1 k minus ui k by delta x. Like this we'll take. So for first iteration, we take like lagging. ui plus 1 is taken to be ui for first iteration. Okay, so after that, I substitute that here and calculate using ui plus 1k. Calculate ui plus 1 k plus 1. And again using ui plus 1 k plus 1 as ui plus 1 k and calculate the new value. So update ui plus 1 each iteration till ui plus 1 k plus 1 minus ui plus 1 k is less than epsilon. So if the difference in the consecutive iterations, if it is less, till then you have to iterate. Okay, so because I am using one old value, one new value, the nonlinearity goes off. Am I clear about this? In ui plus 1 k whole square, I am not taking ui plus 1 k plus 1 into ui plus 1 k. So one is old value, one is new value. That's why the nonlinearity will not be there. So this is one method of tackling it. There is another method, Newton's method. So it is written in general. Suppose I have A, B. Okay, A may be U, B may be dou U by dou X, or it can be A is U and B is U, or dou U by dou X into dou U by dou X, anything. Okay, so A and B are functions of dependent variables. So I have A k plus 1, B k plus 1. So if you take A k plus 1 is equal to A k plus delta A, and B k plus 1 is equal to Bk plus delta B. So this will be Ak plus delta A into Bk plus delta B. So this is equal to Ak Bk plus Ak delta B plus Bk delta A plus delta A delta B. Okay, assuming this is to be small, I will neglect it. And here AK, BK plus AK into delta B is BK plus 1 minus BK. Plus BK into delta A is from this AK plus 1 minus AK. So this will become AK BK plus 1 plus BK AK plus 1. And AK BK, this is one AK BK, this is minus AK BK, here again minus AK BK. One AK BK gets cancelled, so I will have minus AK BK. This is like this. And K are known values, K plus 1 are unknown values. I am multiplying by two unknowns, which is nonlinear. And if this is replaced by this, so here because AK is known, this is not nonlinear. Here because BK is known, AK plus 1 only one is not known, so this is not nonlinear. And AK, BK both are old values, so it is not nonlinear. So this is the way I linearize it. Is it clear?
Yes, sir. Like in the iterative method.
Yeah.
Like why should we use the old value? Like if you are doing iterative method, we can use the same value, right? We not use the old value and new value. We can use the new value in both.
No, if I have both new values, this is in multiplication, right? I cannot multiply two unknown values, which is become nonlinear. Is it okay?
Not in here, sir. In iterative method.
In the iterative method. So what is that?
Like in iterative method, we wrote that ui plus 1, k plus 1 iteration.
Yeah. Actually, I am getting ui plus 1 whole square. So instead of that, I am writing one old value, one new value here.
Like if you are using iterative method, like we need not be afraid of those nonlinear terms, right?
Yeah. Yeah.
And what's the point in converting into linear? Like,
no, I am going to get equations, right?
Yes.
So when I have equations, I want linear one. The unknown values cannot be like ax plus by plus c, ax2 plus by2 plus c2 like that, isn't it? That x, y, z, there should not be square terms in that.
Okay.
Like that. Okay, this is one different ways of linearizing, and we will use some of them in the later schemes. Okay, the next thing, very important thing is stability. Okay, So here, suppose A is analytical or exact solution of partial differential equation, and D is exact solution of finite difference equation. Then A minus D is truncation error or discretization error. Then we come to what is called as N. N is numerical solution of the finite difference equation. Okay, so then D minus N is what is called as round-off error. And let us take this as some epsilon. Okay, here, if I take FTCS scheme, if I write like this, so N, okay, D I will take first. So D is the exact solution of the difference equation. So D has to solve this equation. So DIN plus 1 minus DIN is equal to small d into DI plus 1n minus 2 DIN plus DI minus 1. But N is numerical solution, which I am going to get by solving it. So N also has to satisfy the equation. And if I subtract this from here, so I'm going to get D minus N So like that I will get. What I mean to say is this will become epsilon in plus 1 minus epsilon in is equal to d into epsilon I plus 1n minus 2 epsilon in plus epsilon I minus 1. That is round of error satisfies the numerical scheme. Okay, this is concluded by von Neumann. Okay, in addition to this, he came to this he gave an expression for the round of error. He says epsilon is equal to, it will be varying, the round of error will be varying with exponentially in time and trigonometrically oscillating in x. Okay, so this is e power I, means like sine cos I kmx, cos kmx plus I sin kmx. This is an oscillating variable. It is something like, I'll show you here. Okay, so something of this sort, it will be varying. And so he has written a expression like this, epsilon is equal to e power at into e power I kmx. Okay, so km is called the wave number. like this. So Km is called as a wave number. So this will be of this sort. This is the way he has expressed it. So here, this is epsilon I n. This is epsilon I n. And so here, I want to substitute this in the previous equation, in this equation. So if I have to get epsilon I n plus 1, epsilon I plus 1, and epsilon I minus 1, and like that. So how to get them? Because epsilon I n is equal to e power at e power I kmx. If I want epsilon I n plus 1, so time will be varying. At n plus 1, time is t plus delta t. So this will be e power a into t plus delta t, e power I km x. If I want epsilon I plus 1 n, it will become, because n is same, that is e power at will be as it is, and I plus 1 is there. When I is there, it is x, and when I plus 1 is there, x plus delta x I have to put in the place of kx, e power I km x plus delta x. Similarly, if epsilon I minus 1 n, e power at e power I km x minus delta x I will get. Okay, this is the way I get the expressions for the round of error at any point, at any time. Okay, so these things are to be substituted in the previous formula. So I have got epsilon I n plus 1 minus epsilon I n is equal to d into epsilon I plus 1 n minus 2 epsilon I n plus epsilon I minus 1. And before going to that, actually, what is the stability I will talk about here. Okay, so what is stability is the round of error at any point should not increase as the iterations grow. Okay, so if at a particular point I and time n, it is epsilon I n, in the next time step, it is epsilon I n plus 1. If I take epsilon I n plus 1 and epsilon I n, right? So this is what is called as amplification factor. That is error at a point at a particular time step and error at the same point in the next time step. If you take the ratio of these two, it should be less than or equal to 1. So that is, it will not increase as the iterations grow. So this is the condition for stability. Epsilon I n plus 1 by epsilon I n should be less than or equal to 1. Okay, you can put mod. This is mod. Mod g should be less than or equal to 1. This is the condition for stability. Okay, so this is what I have to prove for any particular scheme. Okay, so if I put here epsilon I n plus 1 is equal to epsilon a into t plus delta t. Okay, in the previous one, some more thing also. So what is epsilon I n plus 1? This is, and this by this, e power a into t plus delta t, e power I kmx by e power at e power I kmx. So this goes off, and this is equal to mod e power a delta t should be less than or equal to 1. Okay, this is what I have to prove for any scheme. Mod e power delta t should be less than or equal to 1. Okay, so now I go to this. E power a into t plus delta t into e power I kmx minus e power at e power I kmx is equal to d into e power a t e power I km into x plus delta x minus 2 e power at e power I kmx plus e power I at e power I km into x minus delta x. Okay, so I substitute like this. And here I divide this by e power at e power I kmx. Divide by this. So what is that I am going to get in the first term? Will anybody help me?
E power delta t. E power a delta t.
A delta t minus
1.
1 is equal to d into e power I km delta x minus 2 plus e power minus I km delta x. Okay. This is the okay, km delta x, you take it as some theta. Okay, so that it will be easy. So d into e power I theta minus 2 plus e power minus I theta. D into e power I theta plus e power minus I theta
2 cos theta.
2 cos theta minus 2. Okay, so it will be like 2d into cos theta minus 1. So if I write this as e power a delta t is equal to, here I will write it as minus 2d into 1 minus cos theta. Okay, 1 minus cos theta, I can write it as
2 sin square theta by 2.
2 sin square theta by 2. Thank you. So I will get this as 1 minus 4d sine square theta by 2. Okay, so this is g or e power a delta t. Now what I have to prove for stability is mod g is equal to mod e power a delta t be equal to mod 1 minus 4d sine square theta by 2 should be less than or equal to 0. This is what I have to prove.
Sir, less than or equal to 1, right?
Yeah, less than or equal to 1. Okay, 1. Sir, thank you. 1. So I will have two conditions. 1 minus 4d sine square theta by 2 less than or equal to 1. This is one condition. Minus of this, that is 4d sine square theta by 2 minus 1 should be less than or equal to 1. Am I clear?
Yes.
So in the first one, 1 goes off. So 4d sine square theta by 2 should be greater than or equal to 0. And what is d? D is alpha delta t by delta x whole square, which is greater than 0, positive. And sine square theta by 2, this is also positive. And this is always true. Okay, I don't have any condition. But if you come to this other one, 4d sine square theta by 2, I take this one to the other side, less than or equal to 2. So if I cancel this, I will have like this. So 2d sine square theta by 2 less than or equal to 1. Or d sine square theta by 2 less than or equal to half. Okay, sine square theta by 2, the maximum value is 1. So this is true if d is less than or equal to half. So this is the condition for stability. Is it clear?
Yes, sir. Like this is the one we told in the last class.
Yeah. FTCS scheme, the condition for stability is d less than or equal to half. So this is the way we have to prove it. Okay, if you will take one implicit scheme. Suppose if I take BTCS implicit. So this is TT is equal to alpha TXX. So we are going to write it IN plus 1. So I'm going to get TIN plus 1 minus TIN. It looks like BTCS only, but on the right side, I'm going to get here all n plus 1 will be there. Okay, like this. So here it will be epsilon in plus 1 minus epsilon in equal to d into epsilon I plus 1 n minus 2 epsilon in plus epsilon I minus 1. So if I see like this, so if I divide this by epsilon in and see what is I'm going to get. So can you tell me what is that I will get here? So because time is there, I will have e power a delta t. Okay, because n plus 1 is there. And here it will be 1. This is equal to 2d into, here in space 1 is there, plus 1. So e power a delta, both are there, n plus 1 is there, here also. So e power a delta t will be there, and also e power ikm delta x will be there, right? Minus 2, here in time it is e power a delta t, plus here also. So e power a delta t, e power minus ikm delta x. Because everywhere here these are n plus 1s are there, so I will have e power a delta t extra compared to FTCS. Is this equation clear?
Yes, yes.
So I can take e power delta t common here. So I'm going to get similar to the other thing like e power ikm delta x minus 2 plus e power minus ikm delta x. Okay, so here so this is d e power a delta t into again 2 cos theta minus 2, that is 2d e power a delta t into cos theta minus 1 or 4d e power a delta t sine square theta by 2. Just like the previous one, only thing this additional e power a delta t will be there. So I have e power a delta t on both sides. I have to bring it to the left side. So e power a delta t into 1 minus 4d sine square theta by 2. This 1 I will take it to the right side. This is equal to 1. So now I will get e power a delta t is 1 by 1 minus e power a delta t is equal to 1 by 1 minus 4d sine square theta by 2. So can I tell this it is less than or equal to 1 for any value?
It's always greater than 1.
This is it okay? 1 plus, I think, just one previous one. This is minus, right? Cos theta minus 1, this will be minus, and this will be plus. This will be plus. So it will be like this. Okay, for whatever value of d and theta, 1 by more than 1 is there. Am I clear?
Unconditionally stable.
So this is always less than or equal to 1. So that's why this is unconditionally stable. So this is the way we have to prove for any scheme. Is everything clear? Okay, so this is the things that I wanted to cover today. We have seen the consistency, how to find out the consistency condition, and we have seen the linearization, how to linearize a nonlinear term, and there are 3 methods we have seen, and then we have seen Von-Neumann stability analysis. Okay, so using this, we can find out any scheme, whether it is stable or unstable, or whether it is conditionally stable or conditionally unconditionally stable or unconditionally unstable also we can check. Okay, if it is always greater than or equal to 1, then it is unconditionally unstable. Okay, suppose here instead of 1 plus, if I have 1 minus, so what happens is this will be always less than or equal to 1. And so this 1 by this will be greater than or equal to 1, then it will become unconditionally unstable. So that is the way we have to prove. Is everything okay? If everything is okay, we will go to the story.
Sir, like, can you go 7 slides back?
Yeah, sure. Slides or this written?
Yes, the written part.
Okay. Is it this? Which one?
Once go to previous one. Sir, here my doubt is like, what is the difference between exact solution and numerical solution of finite difference? Like,
yeah. Exact solution is the exact finite difference equation, which is to give something. But when I'm using computer, right, because of the round of error, I may get a different solution for that.
Yes.
Numerical solution.
But does exact solution always have to exist for that finite difference equation?
Exact solution?
Like, is it necessary for that to exist always?
Yeah, a finite difference equation is there. It will have some solution, right? And depending on the computer, you will get minimum round of error and you will get the exact solution. An exact solution will have one solution which is exact solution.
Okay.
If I suppose use some method to find out the solution without a round of error, that is the exact solution. Okay.
Yes, sir.
Right.
Next slide, sir. Next slide.
Yeah, sure.
Here, okay. Here it is okay. Next slide. Yeah, like here we are defining a complex term, right? Epsilon I power and in is equal to EAT. Like it doesn't have to be.
We should not say it is complex. Okay. It's complex only. Cos theta plus I sin theta. It is like trigonometrically varying. Okay, you can see the reasoning in Anderson book. You can just check. Okay. If you have any doubt, we will discuss about it.
Okay. That's it.
Right. Okay, we will see today's story. It is a small touching story.